Good afternoon, all my dear students. Welcome to the another topic in the Unit 1, that is chemical properties of the first transition series. As we have learned, the transition elements are divided into the four series. First series, that is 3D, then second 4D, then third 5D, and the fourth one is 6D. We have read about the general characteristics and the periodic properties of the first transition elements. Now we talk about the chemical properties of the first transition elements. It includes the 10 elements. It starts from 21 atomic number to 30. In this lecture, what are the prerequisites required? The student should have the knowledge of the first transition series, its characteristics and the properties, including the binary compounds like oxides, sulfides, halides of the first transition series. In this lecture, we are going to cover the following topics: the complex compounds of the first transition series, what is the coordination number, the geometry of the complexes, relative stability of the oxidation state, and the colored ions formation. So these important points we will discuss in this lecture. What is the learning outcome of this lecture? The students will be able to understand about the chemical properties in which we focus on the complex formation tendency of the first transition series and the relative stability of their oxidation states. So let's start. The first property we should discuss about the complex formation. Okay, the element of the first transition series fulfill all the conditions of the complex formation, and they are most suitable for this purpose because it is an important property of the transition elements, and the general representation of the complex of the first transition series is this, like MLN X plus minus. What is M? M is the transition metal. The N represents the number of the lone pair accepted by the central metal atom or the ion from the ligand L. So here Ln means the number of the lone pair the ligand donates to the central metal, that is transition element, and X is the charge on the metal complex, which can be positive or negative or even zero. Here you can see the positive and the negative charge, where we can express it in the form of X, but it can be zero in the neutral complexes. All the elements of these series form the complex with the variety of the ligands. Here you can have the example of the complexes like chromium, here the transition metal which forming the complex with the ligand, the water and the chlorine ion, here the cyanide ion, ammonia. So variety of the ligands, the neutral ligands, anionic ligands, as well as cationic ligands. So they show the formation of the complex with the variety of the ligands. The element of these series form the stable complexes with the nitrogen, oxygen and the halogens, the donor ligands. So in the complex, what is the coordination number? The number of the ligand, specifically the monodentate ligand, which is having the one donating sites. when directly attached to the central metal atom, or more appropriately the number of the lone pair of the electron which is accepted by the central metal atom or the ion from the ligands in the process of formation of the complexes is known as coordination number of the metal. So we have the example of this complex of the silver. That is the coordination number of the silver here, because it is attaching with the ligand. Here the ligand is ammonia. So this is L, this is M, okay, this is M, this is L, and how many number of the L is there? That is N. Okay, we have in the general formula N, and that is the charge 1 positive, that is X. So here it is the monodentate ligand ammonia, so which is attaching the number. How much number of the ammonia is donating to the central metal atom silver? That is 2. So here the coordination number is 2. Okay. Similarly in the copper, what is the coordination number? It is similarly forming the complex with the ammonia. That is also how much? 4. And what is X value here? X value is 2. 2 positive. And here what is the coordination number? Here the iron is the central metal atom. What is the coordination number? Can anybody? Yeah, definitely. It is 6. So the central metal atom or the ion attached to the ligands are kept within the square brackets, which is called the coordination sphere. Okay. So this you can see. What is this? This type of the brackets. This is the square brackets. Okay. So always the complexes are there, including the central metal atom with the ligand in a coordination sphere, and with many of the polydentate ligands when it form the complex. It is a simple complex forming by a single ligand, the monodentate ligand. If we have the polydentate ligand have many sites to donate the lone pair of the electrons, so that type of the complex form a ring type of the complex which is called the chelates, meaning the claw, the crab's claw. Like the crab's claw, the central metal ion being trapped by the ligand. Okay, so this in detail we talk about the coordination number and the complexes in the coordination chemistry. But here the main property we are talking about the transition element, that is the complex formation. The variety of the complexes are formed by the transition elements. So now let's stand the geometry of the complexes. The geometry of the complexes depend on the coordination number, as we have seen, of the central metal atom or the ion. So it will decide the geometry. If the coordination number is 2, the geometry is linear. Generally the complex with the oxidation state, the copper 1 plus, silver 1 plus, it generally form the linear complexes. Okay, and if we are having the coordination number 4, we are having two type of the geometry. The one is tetrahedral and another one is square planar. With the coordination number 4, we have two geometries of the complexes. Manganese of the first transition element, cobalt, iron, nickel, and copper 2 plus. Okay, complexes with the weak ligands like water, we have a chloride, bromide, iodide, iron, halogen. So with this it forms with the weak ligands it form the tetrahedral geometry, and with the strong ligands it form the square planar geometry, like nickel copper complexes with the strong ligands. Here you can see ethylene diamine, ammonia, and the cyanide ion. So according to the strength of the ligand, whether they are weak and strong, and we will talk about this strength of the ligand in the coordination chemistry, but here you have to remember, because the first transition elements with the weak ligands, so certain transition elements like manganese, cobalt, iron, nickel, they form the complex with the weak ligands, which is having the tetrahedral geometry, and forming the strong ligand, it is the square planar. If the coordination number 6, the octahedral geometry is there always. So chromium, manganese, iron, cobalt with is forming with the weak and strong field ligands. So chromium, manganese with a higher oxidation state, they form the octahedral complexes. Now we talk about the relative stability of the oxidation state of the first transition series. The stability of the element is determined by the electronic configuration. You know the electronic configuration of these first transition elements. So we can see that in 3D series it exhibits the variable oxidation state, and we have the oxidation state goes on increasing up to the middle element, and then it goes on decreasing. Its order we have seen. Now if we compare the higher oxidation state and the lower oxidation state stability, the higher oxidation state stability is more than the lower oxidation state. So if we have this order of the higher oxidation state is 4 in titanium, and here the 3. So 4 is highly stable than the 3. Here also the 3 is there in the ferric ion, then the ferrous ion. Generally the lower oxidation state are less stable than the higher oxidation state. Now if we understand why this is so, the stability depends on many factors. On the basis of that, it can be said. So let's see what are that factors. So if we see what are the factors, the first factor is filled, half-filled and vacant d orbitals. If it is present in this compound, like fully filled is D10, D5 is half filled, and D0 configurations are more stable than the other configurations. If we see the titanium 4 plus, if 4 electrons it donates, what will be its electronic configuration? D0. D0 is stable or not? Yes, D0, that is vacant d orbital, which is stable. That's why titanium 4 higher oxidation state is more stable. That is the order we have seen previously. Then we have what? The 3. What is its electronic configuration? One electron will remove. That becomes D1. Mn2 plus. That is more higher oxidation state, that is of half filled. Then this D4, it is not stable. D4, D5 is more stable, but we can't say it is always true. The copper, we have the 3D10, which is less stable than the Cu2 plus, that is 3D9, due to the high lattice energy and the solvation energy in the solid state and in the solution. If it is having high lattice energy, it is more stable, no? Even the solvation energy. So we cannot say only one of the factor, that is the electronic configuration, decides the stability of the oxidation state. Yeah, it is one of the factor, but other factors can dominate over the factors which can decide which oxidation state is stable. So the other come with the lattice energy and the solvation energy. Higher oxidation state become less stable as the atomic number increases. So if we see the atomic number goes on increasing, the higher oxidation state become less stable. So let's see here, scandium, titanium, vanadium. It goes on increasing the atomic number. And as the atomic number from the left to right, it is the order of left to right in the period. Yes, scandium, titanium, vanadium, chromium, manganese. So as increasing the atomic number, as we found, the oxidation states, it goes on less stable, even if they are higher oxidation state. By increasing the atomic number, their stability decreases. The relative stability in the binary compounds of the 3D series. It can also be understood by the halogens and the oxygen atom attached to the transition metal. So the group of the oxidation state of many of the elements can be understood how the oxygen atom can be more readily attached to the transition metal than the halogens like fluorine, the strongest halogen. And this can be understood that fewer oxygen atoms are only required than the fluorine atom to achieve the same oxidation state. If we have one example of the manganese with the higher oxidation state, +7, okay. So how it can be achieved? It can be achieved with a fewer oxygen atom, like MnO4 negative. Oxygen number of atom is required 4 to achieve this oxidation state. It cannot be stable more with the fluorine, because fluorine require more number of fluorine atoms is required to stabilize this oxidation state, and it is required about 7, which is higher, and that's why it's never been stable. So this also one of the factor we can understand the stability, how the oxidation state can be stabilized with the fewer number of atoms. The another factor in the D block elements, the oxidation state can be stabilized by the complex formation. The low oxidation state are less stable, and the ligands like cyanide and nitrogen, nitrosyl, carbonyl are called pi acceptors, forming the complex in these low oxidation state. So they stabilize them, and such type of the complexes we can say are called pi complexes to stabilize the lower oxidation state, and higher oxidation state are stabilized by the complex formation with the high electronegative atom like halogens. Now we talk about the another property of the transition elements, that is colored ions. The compound or the ions of the transition elements appear colored. Why? It is due to the two important reasons: the d transitions and the charge transfer. why the compounds of the transition elements appear colored, even the ions. That is the important property. It is due to the two factors, that is DD transition and the charge transfer. So the DD transition, we can understand the compound may appear colored if the electrons in one energy level absorb the radiations in the visible region to get excited in the another energy level. And how it happens? When the ligand approaches towards the central metal atom having the d orbitals. How many d orbitals are there? 5 d orbitals are there. So when the ligand approaches, the d orbitals get splitted into the two parts. Here you can see the 5 d orbitals get splitted into the 3, that is T2G at the lower level and EG goes to the higher level. So this is called DD splitting. And the electron, when absorb the radiation in the visible region, it transit from this lower level T2G to EG, which is responsible for the appearing colored, understood, during this possible transitions, which is found in the transition elements. These two sets differ in their energy. Electron absorb the radiations in the visible region in the low energy and excited to the higher energy level. And in this way, the color depends on DD transition. Higher the transition in an ion and darker its color. And for the DD transition, it is very essential that the transition element should have the unpaired electron in it. So if it is having the unpaired electron, the color of the compound or the ion is due to the DD transition. The next reason is of the charge transfer in such a compound where the DD transition is not possible. Like for example, this manganese oxide, chromium oxide, lead oxide, tin, because they are not having the unpaired electron. So DD transition cannot be possible in these ions and the compounds. So why they appear colored if the DD transition is not found? In these ions, the electrons get excited from the orbital of one atom to the orbital of another atom by absorbing the radiations and giving the dark color. So the transition of the electron occurring in UV region is called charge transfer transition. So we can say this kind of the charge transfer transition is found in the transition elements like this manganese oxide. Here what happened, the electron of the orbital of the oxygen atom goes on transition to the manganese. So this is the arrow here showing oxygen atom is going to the chromium. So this is the charge transfer from the ligand to the metal ion likewise. So it is responsible for the colored ions or the transition compound which appear colored. These are the references of the topic. We have taken the chemical properties of the first transition series. You can take the references from these are the textbook and the reference book which you can follow. So we talk about the another chemical property in the next lecture. Till then, thank you and take care.